What I wanted to do on today's episode was complete the printed circuit board layout that we've been working on over the past 3 episodes. But as I was preparing for this, I ran into a slight problem. Actually, I'm not going to call it a problem. I want to call it an opportunity. You see, we've been so focused on printed circuit board for the last few episodes that all of the hardware that we designed, specifically the actual LED lamp or the place where the LEDs are mounted to, it's kind of been sitting aside over the past few weeks or even months. And when I went to try to turn it on, it didn't work. And after a little bit of investigation, I realized I had a short circuit. And so I thought maybe I'll focus this episode on sharing how we resolved that short circuit, and we're going to prevent it from happening again. It was way back in episode 10 when we actually built that LED panel. You remember when I took those 3 high-powered LEDs and affixed them to this metal backing plate that was mounted on a wooden block, and then I took the LED driver MOSFET and I screwed it into that same block? Well, at the time, it was a great idea. Turned out it's not such a good idea because it opens up the potential for a short circuit, which is not disastrous, but somewhat unpleasant. Take a look. Here's that LED panel that we built. You can see the 3 high power LEDs that are affixed to this metal backing plate, and then the whole thing is mounted on a wooden block, and these 4 screws are keeping the whole thing together. The 5th screw is holding this MOSFET down, and you can see the plus 12 volts supply coming in over here, which exits the other side of that LED string, goes into the source of the, or the drain, sorry, of the MOSFET, and then the gate and source of that MOSFET go back to our circuit over here. Now, at the time, it seemed like a great idea to use that metal plate as a heatsink for both the LEDs and the MOSFET. But if you remember, the drain of that MOSFET is also connected to that heatsink. So what that means is this entire backing plate is effectively the drain of the MOSFET. So it's electrically connected to the system. And take a look at the way I've wired this thing up. This plus 12 volts is coming awfully close to that metal plate. So I powered up the circuit and cranked up the intensity of those LEDs. But there was no light. The LEDs were not emitting anything. But I looked at the power supply and I noticed that it was still pulling more than 300 milliamps, but no light was being generated. What happened? Well, it turned out that all of that energy was being dissipated by this MOSFET. So I've got one of these cool laser heat guns that allow me to point it at something and check the temperature of that surface. And so I did that. I knew my LEDs were shorted, and so I turned the circuit on, put the intensity at maximum. I pointed this to the MOSFET, and I checked the temperature of the MOSFET. Take a look. It took about a minute for this thing to increase in temperature from roughly 20 degrees Celsius to 30 degrees Celsius. And I'm sure if I left it on running, it would just continually go up. Back in episode 9, one of our objectives was to figure out how much energy could potentially be lost as heat in our circuit. And back then we calculated that each one of those LEDs would consume about 1 watt of energy. So 3 LEDs, that's 3 watts. We also figured out that this MOSFET could potentially burn off as much as 1 watt. So anywhere from 0 to 1 watt. So in this situation, since we have a short circuit, all of those 3 watts that were intended for the LEDs are now being forced through that MOSFET because we've created a constant current LED driver. It's going to continue to push 350 milliamps, and our circuit is running at 12 volts. It's going to bring it up to about 4 watts of heat being generated in that MOSFET. So even in this situation, because our MOSFET is securely attached to that heatsink and it can handle up to 8 watts of power, we should be fine. But practically speaking, as we move forward, we're going to want to minimize all this to a smaller area. We're certainly not going to be mounting our LEDs on wooden blocks. And chances are we're going to have multiple drivers very, very close to one another. So I certainly don't want this much excess heat energy to be wasted in case there's a short. So the 2 things that I want to do is I want to build in some sort of a short circuit protection, which will cut off the current if it detects a short circuit. And second, I want some sort of an indicator to let me know that, hey, you're in a short circuit state right now, and we need to fix it because there's a problem. So 2 things we want to embed into our circuit today. Let's start by taking a look at the circuit that we have right now for our LED driver. This particular circuit shows a 5-bit LED driver, which, if you remember, 5 bits will give us up to 32 levels of intensity. You can see we have our plus LED and minus LED. So these two leads will head out to the string of 3 LEDs in series. And over here we have our plus 12 and our ground. Now, when the circuit is powered up and running, all of the current that flows through those LEDs returns to our circuit from this LED minus lead over here. So all we really need to do is figure out when a short circuit is happening. And when that short circuit is happening, we need to cut off this MOSFET. And we can do that by bringing the gate down to 0. Now, as you might imagine, there are lots of ways to implement this. The method that I wanted to use was I wanted to employ the use of a Zener diode. There is plenty of great resources out there, but the short and simple version is really easy. If you remember back in episode 3, we talked about this concept of how a regular diode works and how the voltage needs to be over a certain value until the current can flow. If the voltage is less than that value, no current's flowing. If the voltage is over at that value or over, then current begins to flow. Well, a Zener diode is similar, except that you can have a very tight control or very precise control of what that Zener voltage is. And using the analogy that we made up in episode 3, the height of our wall. So by using a Zener diode, we can very accurately or precisely create a wall such that when the energy or the voltage is over that value, over that wall, we now want our circuit protection to kick in. So when the voltage that we're sensing exceeds this certain threshold value that we can set, the current will begin to flow through this Zener diode. And what we want to do with that current is use it to trigger a cutoff for our main MOSFET. And we can use a BJT transistor to do that. Let's take a look at the circuit and see how we can build this. So the first thing that I've popped in is this BJT transistor over here. The collector is connected to the gate of the power MOSFET, and the emitter is connected to ground. So all we need to do is ensure that there is a current flowing through that base when we detect a short. And in order to detect that short, let's use the Zener diode. Here it is over here. Now the Zener diode looks a lot like a regular diode, except it's got these two little fancy little wings on the cathode part. And you'll also notice that it's connected, it appears to be connected in reverse. That's because a Zener diode is designed to work in reverse bias. So the way this Zener diode is designed to work is when this voltage right at this point exceeds a certain value, it will allow current to flow through this lead. And if there's current flowing through this lead, then that's going to activate this transistor, which is going to cut off this MOSFET over here. So these two resistors we're going to set up to be a voltage divider. So we want to make sure that this resistor is, 10 times higher than this resistor. And we're going to choose the appropriate Zener voltage so that this will trip at the right point. But before we go and choose our components, I want to add the indicator in here as well. So we'll pop it in over here. This is the indicator LED that will turn on whenever we've detected that we have a short. And you can see that we've simply popped in yet another one of those BJT transistors over here through this resistor, which is going to limit the current for this indicator LED. So how do we know what value of Zener diode to use? Well, that's an important question because what we're trying to do is we're trying to prevent a short circuit condition. And in a short circuit condition, we have somewhere around 12 volts sitting at this point over here. And what we want is we want current to be flowing through this path in order to trigger these BJT transistors. Now, what we know about BJT transistors is that it takes about 0.7 volts across the base and emitter to get a current flowing through them. And since we got two of these BJT transistors connected here, that means that the voltage here must be at least 1.4 volts. And because of this voltage divider that we have set up over here, RS1 is going to be 10 times higher than RS0, then the voltage at this point needs to be, 1.4 plus 0.14, which is 1.54, I think, 1.54 volts over here. So that basically means that in order for this circuit protection to be triggered, this value or the voltage value right at this point behind the Zener diode or at the anode of the Zener diode needs to be 1.54 volts or greater. And in that scenario, we'll start to get current flowing through this. Now, I happen to have a 10 volt Zener diode here. So a 10 volt Zener diode in this circuit would mean that this would actually start conducting at 1.54 plus 10. So it'll be 11.54 volts. So as soon as the voltage reaches 11.54 volts, the indicator light will turn on and the short circuit protection will be active. So I think the 10 volt Zener diodes will work. Let's go ahead and use these. So here's all the components already laid out on the breadboard. You can see all of the extra circuit protection components built in. We have our little diode over here that's going to let us know when our circuit protection system is activated. And here's the Zener diode. So it's a bit messy because I actually have this lead poking out over here, and the other end of that lead is connected to the other end of our LED. I had to do this because our MOSFET is actually soldered or secured still onto this board. When we progress to the next phase of this, we're going to disconnect that and we won't need this big ugly lead. Let's test it out and see what happens. So as I turn this on, we can see that the lights turn on and the current draw is as expected. And then when I go ahead and short it, the current usage in our circuit has gone down to nothing. When I release it, the short, it jumps right back up to where it's supposed to be. I am so happy that we encountered this problem before we went ahead and designed our PCB. Now that we did this, we can build in the circuit protection and the indicator into our PCB design. We're going to do that on the next episode. See you then.